Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome back to today's deep dive. If you are joining us right now, learner, we know you are always on the hunt for that next big aha moment.
Oh, absolutely.
You love pulling back the curtain on how the world actually works. And today, we are going to change exactly how you look at, well, like every single bottle sitting in your kitchen pantry.
It is great to be here. We are looking at a really fascinating piece of research today. It's a paper titled Biocatalytic Platform for Functional Edible Oils.
Which is quite the mouthful.
It is, yeah.
Yeah.
But what this paper outlines is just, it's nothing short of a revolution in food science and bioengineering.
Exactly. So the mission for our deep dive today is to explore this cutting-edge blueprint for taking incredibly cheap, abundant agricultural seed oils, the stuff produced by the millions of tons globally. And we're talking about literally hacking them at a molecular level. The goal here is to give them the health benefits, the stability, and the nutritional profile of premium, highly expensive oils.
Making commodity seed oils perform exactly like extra virgin olive oil or avocado oil in your body.
Yeah, which is wild. And we should probably set the stakes here for you, the listener, because this touches on a massive global issue. Right now, there's a fundamental nutritional inequality when it comes to the edible oils we consume.
For sure. Premium oils, the ones with those highly favorable fatty acid profiles and rich natural antioxidants, they are just incredibly expensive.
Yeah.
They are supply limited, and geographically, they're super concentrated. You can really only grow olives and avocados efficiently in very specific temperate climates.
Meanwhile, on the other end of the spectrum, you have your commodity seed oils. Think soybean oil, sunflower oil, certain canola streams. And we have to be clear here, these commodity oils are not the villain.
No, not at all.
They are a miracle of modern agriculture. They grow in a huge variety of regions. They are incredibly abundant, and they are totally vital for feeding a growing global population affordably.
That is such a crucial point. They are an economic and agricultural triumph. But nutritionally speaking, compared to those premium oils, they're just suboptimal.
Right.
These simply do not offer the same cardiometabolic benefits or, oxidative stability.
Right. And the solution proposed in this paper isn't just casually mixing a cheap oil with an expensive one to stretch out the supply.
That would be way too easy.
Yeah. Instead, they propose what they call a modular biocatalytic platform. It involves using natural enzymes and specialized microbes to literally redesign the fats of these cheap oils from the ground up.
We are fundamentally altering their molecular architecture.
Right. So to understand how wild that is, we first have to understand why these cheap commodity oils are considered structurally inferior in the first place.
Yeah, and it actually comes down to the architecture of the fat at a microscopic level. It is not just about the total list of ingredients or fatty acids in the oil. It is about where those specific ingredients are physically placed on the molecule.
Okay, let me try an analogy here to make this visual for the listener. Imagine a fat molecule, which scientists call a triacylglycerol, or TAG for short.
Right, a tag.
Imagine it as a three-seater couch. When you look at an oil's nutritional profile, it is not just about who is sitting on the couch, it is about where they are sitting.
I love this analogy.
Right, so the outer two seats are important, but the absolute most critical spot is that middle seat. In biochemistry, they call that middle seat the SN2 position.
That is a perfect way to visualize it, because the human digestive system processes that middle seat very differently than the outer two seats.
Oh, really?
Yeah, enzymes in our gut tend to clip off the fatty acids on the ends, but they leave that middle SN2 position entirely intact.
So it just goes straight through.
Exactly, allowing it to be absorbed directly into our bloodstream.
Okay, so for an oil to give you the absolute best digestion and the best cardiometabolic health benefits, that middle seat really needs to be occupied by a very specific VIP guest.
Yes.
And that guest is oleic acid.
Exactly. Oleic acid is this highly beneficial monounsaturated fat. In premium oils, like olive oil, oleic acid is heavily enriched right there in that middle seat.
So it's perfectly positioned.
Right, perfectly positioned for your body to absorb and utilize it for heart health. But in commodity oils, like your standard soybean or sunflower oil, you have the completely wrong guests occupying that VIP space.
They've got the unruly, unpredictable guests sitting right in the middle.
Precisely. Commodity oils tend to have an excessive amount of polyunsaturated omega-6 fatty acids, specifically linoleic and linolenic acids. They just hog those crucial SN2 positions.
Wow.
And this poor positional layout doesn't just affect human metabolism. It fundamentally ruins the physical stability of the oil itself.
Meaning it goes bad faster, like it breaks down in the pan.
Yes, it leads to very poor oxidative stability.
Mm.
When you have too much polyunsaturated fat, those omega-6s in the wrong spots on the molecule, the oil is highly prone to oxidation.
Oh, I see.
It breaks down rapidly under heat, it goes rancid on the shelf much faster, and it simply does not have the cardiometabolic advantages associated with the monounsaturated rich premium oils.
So the problem isn't merely that cheap oils have the wrong overall ratio of fats, it's that they have the wrong structural blueprint entirely.
Exactly.
Okay, let's unpack this. If we know the seating arrangement on this molecular couch is the root of the problem, how do we actually fix it? Because we can't exactly use tiny tweezers to move billions of molecules around.
Definitely not.
And the paper makes it clear we want to completely avoid using harsh chemical processing. So let me offer a specific pushback here.
Sure.
If the end goal is just to get a better fatty acid profile, why go to the immense trouble of using complex biological tools to rearrange molecules? Why not just take a massive industrial vat of cheap soybean oil and blend it with a little bit of premium olive oil to sort of average it out?
Well, what's fascinating here is the difference between crude blending and design by structure. If you just blend the oils, you aren't actually fixing the structural problem of the cheap oil at all.
Oh, right.
You still have those unstable omega-6 fatty acids sitting in the wrong SN2 middle positions on their respective glycerol backbones. You haven't changed the melting behavior, the crystallization, or the fundamental oxidative stability of the cheap oil.
You've just diluted the bad couches by adding a few good couches into the room.
Exactly. The structural weakness is still there. The bad couches are still going to break down when you heat up the pan.
I see.
And this is where the first major pillar of this new bioprocessing platform comes in. It's called enzymatic lipid structuring. Scientists are using highly specific enzymes called lipases to selectively rearrange the fatty acids on that glycerol backbone.
Okay, so lipases.
Right. It's a process called enzymatic interesterification.
Enzymatic interesterification. Say that 5 times fast.
It is a total mouthful,
Yeah.
but is a highly mature and environmentally attractive route.
Yeah.
Think of these lipases as highly specialized ushers at a theater.
Yeah.
They can precisely pluck a fatty acid from one seat and swap it with another, creating very specific structured lipids. The paper refers to configurations like MLM or MLL tags.
Wait, let me stop you there. MLM. What do those letters actually stand for in our couch analogy? Because right now it sounds like a multi-level marketing scheme for fat molecules.
Fair point, yeah. The letters refer to the chain length of the fatty acids sitting on the couch. M stands for medium-chain fatty acids, and L stands for long-chain fatty acids.
Okay, so an MLM molecule has a medium-chain fat on the left, a long-chain fat in the middle, and a medium-chain fat on the right.
Exactly. And the reason this is so groundbreaking is because of how our bodies process different chain lengths.
That's so.
Medium-chain fats, the M's on the outside seats, are burned very quickly by the liver for immediate energy. They don't typically get stored as body fat.
Nice.
Meanwhile, that long-chain fat in the middle, the L, which we designed to be our VIP guest, oleic acid,
Right.
that is absorbed intact for those long-term cardiometabolic benefits.
That is incredible. So by using these enzyme ushers, we were basically custom building the perfect fat molecule that gives you quick energy on the outside and heart-healthy oleic acid on the inside.
Yes. And because these are biological enzymes doing the work, they do this rearranging with incredible precision. They don't create the toxic side products or trans fats you would get if you tried to force this reaction with harsh industrial chemicals.
So the goal here isn't just imitation, but creating specific nutritional performance.
Exactly.
So by using these enzymes, we dramatically improve the ratio of monounsaturated to polyunsaturated fats. We force that beneficial oleic acid right into the SN2 middle seat.
Yep.
And the result is that the oil's frying stability skyrockets. Its shelf life is vastly extended. Its thermal behavior improves. We literally take the base materials of a cheap, abundant seed oil and rebuild them into an olive-like profile.
That's the first half of the puzzle solved, yeah.
Here's where it gets really interesting, though. Because premium oils aren't just fat. The reason extra virgin olive oil is so highly prized isn't solely its fat structure, right? It is also packed with powerful, naturally occurring antioxidants.
Oh, absolutely.
So how do we get those premium antioxidants into our structurally fixed cheap seed oil? Because rearranging the couches doesn't magically create antioxidants out of thin air.
You are entirely right. And for that, The paper introduces the second major pillar of the platform, which is microbial functionalization.
Okay, microbial functionalization.
Right. We had to shift from enzymology to microbial metabolism, specifically using oleaginous, meaning oil-producing, food-compatible microorganisms in yeasts.
This is such a fascinating concept. I like to think of these microbes as tiny, highly specialized breweries. You drop them in, and they basically brew up and infuse the newly restructured oil with the exact protective compounds you would normally only find in nature's best oils.
The brewery analogy is perfectly accurate, and the compounds these microscopic breweries are churning out are incredibly valuable.
Like what kind of compounds?
We are talking about carotenoids, sterols, tocopherols, and phenolics. The nutritional impact of a premium oil is never just about the fatty acids alone. It is these minor compounds that do the heavy lifting for oxidative stability and the actual biological value of the oil in your body.
And the paper outlines two different ways these microscopic breweries can be utilized, correct?
Yes, there are two distinct engineering routes here. You can do it upstream or you can do it adjunctively.
Walk us through the upstream route first.
Upstream microbial functionalization means you grow these oleaginous yeasts in separate massive fermentation tanks. And the beauty is you can feed them low-cost agricultural residues.
Basically plant waste.
Yeah, plant waste. The yeast consumes the waste, grows, and naturally accumulates these antioxidant-rich fractions inside their cells. Then you harvest the yeast, gently extract those valuable antioxidants, and physically blend them into your structured seed oil.
Okay, so that's like brewing the good stuff in one building and then mixing it into the oil in another building.
Right.
What is the adjunctive route?
The adjunctive route is far more radical. This means using the microbes to directly biotransform the oil streams themselves. You can introduce the yeast directly into the oil, and you use controlled fermentation to enrich the oil with things like hydroxytyrosol-like phenolics right there in the tank.
Wow. Okay, I have to be honest here. As a consumer, hearing that yeast is actively fermenting inside my cooking oil sounds like a recipe for a rancid kitchen.
I know, it sounds a little off-putting.
How on earth do they strip the fermentation smell out of the final product? Because nobody wants their salad dressing to taste like a brewery floor.
That is exactly the primary scientific hurdle. Getting the microbes to produce the compounds is the easy part.
Right.
We've known they can do that for decades.
Right.
The critical challenge is ensuring these microbial compounds actually integrate into the edible oil matrix in a way that works for human consumption. It has to have an acceptable flavor profile, it has to remain stable during prolonged storage and high-heat cooking, and of course, it has to meet extremely strict regulatory compliance.
So they have to find a way to clean it up without destroying the antioxidant.
Precisely. The translational path from a successful laboratory experiment to a product in your kitchen requires what scientists call compositional reproducibility.
Meaning, the factory needs to be able to make it taste and behave the exact same way on a Tuesday as it does on a Friday. No unpredictable, funky batches.
Exactly. It has to work flawlessly in real, everyday culinary use.
So, what does this all mean? We now have a perfectly structured, antioxidant-rich oil sitting in a laboratory beaker. It has the perfect structural couches for digestion, and it has the premium antioxidant seasoning brewed in from our microscopic yeasts.
Yeah.
But how do we actually manufacture this at a global scale without completely destroying it? And furthermore, does it make any economic sense? Because earlier we talked about how commercial biocatalysts, enzyme ushers, doing the molecular rearranging are still incredibly expensive at scale. Does this sci-fi oil actually make financial sense compared to just growing more olives?
That is the multi-million-dollar question. And it brings us to the crucial topic of downstream processing and the techno-economic analysis, or TEA.
The CEA.
Right. You are entirely right to be skeptical. You can have an absolute miracle product in a beaker, but if the economics don't work, it will never reach the consumer. The process engineer's absolute mantra here is that preservation is just as important as synthesis.
Meaning, don't destroy the incredibly valuable, delicate thing you just spent so much time building.
Exactly. Let's look at standard industry practices. Normally, commodity oils are blasted with harsh chemical solvents, like hexane, to extract as much yield as possible.
Hexane, yikes.
Right. Hexane is highly efficient and boils away easily, but that aggressive process would completely obliterate all those sensitive carotenoids and phenolics the microbes just carefully brewed for us. The heat and the harsh solvents would erase all the functional value we just built.
So the factory itself has to be entirely redesigned to be gentle. How do they actually do that?
Well, the platform requires processes like solvent-lean purification, membrane separations, and mild distillation.
Wait, explain membrane separation for us. How does that work compared to chemical solvents?
Instead of chemically stripping the oil, membrane separation acts like a microscopic bouncer at a club.
Oh, I love that.
You gently push the oil mixture through a highly engineered, semi-permeable physical barrier. This membrane has pores so unbelievably tiny that it physically filters out the impurities based on their exact molecular size, while gently allowing those delicate heat-sensitive antioxidants to pass through completely intact. No extreme heat, no harsh chemicals.
That makes perfect sense. So the downstream manufacturing train has to be an integral part of the initial product design, not an afterthought.
Exactly.
Now, regarding the economics, you mentioned the techno-economic analysis. How do the numbers actually play out in the real world?
The literature usually compares 3 distinct manufacturing scenarios to see if this platform is commercially viable. Scenario 1 is the status quo, the direct sale of commodity oil. It is incredibly cheap to do, but it relies on razor-thin margins. You are making pennies per gallon, and the product is nutritionally poor. It is just a race to the bottom.
Okay, and what is the second scenario?
Scenario 2 is partial upgrading. This means entirely skipping the microbes and using just the enzymatic structuring to fix the tag architecture, rearranging the couches.
Got it.
It improves the health profile and stability significantly, but it doesn't add the premium antioxidants.
And scenario 3 is the whole 9 yards, right?
Correct. Scenario 3 is the full package, enzymatic structuring, plus full microbial functionalization with bioactives. Get the perfect fat structure and the premium antioxidants.
But scenario 3 has to be unbelievably expensive to set up. I mean, you need enzyme reactors, massive fermentation tanks for the yeast, complex, gentle membrane filtration systems.
It requires hundreds of millions in initial capital expenditure, yes.
Hmm.
And that brings us to the trade-offs, which one actually wins out. The economic secret here is that viability relies heavily on process intensification.
Process intensification.
Right. This means running continuous operations, rigorously reusing those expensive enzyme ushers over and over again, and minimizing the cost of preparing the oil beforehand.
So if scenario 3 is too expensive right now, does scenario 2 hit the sweet spot?
Frequently, yes. The highest value product isn't always the most complex one. It is the one that perfectly balances nutrition, manufacturability, and regulatory simplicity.
That makes a lot of sense.
Scenario 2, continuous enzymatic processing using crude oils, often provides the most material improvement in both sustainability and economics without triggering massive regulatory hurdles. But the real economic advantage of all these scenarios is the starting material. Low-cost, regionally distributed agricultural seed feeds are everywhere. You aren't paying a premium to ship olives across the ocean.
Right. You are taking whatever cheap seed grows natively in your specific region and upgrading it locally. That is a massive logistical advantage.
Exactly.
Okay, we need to take a step back and look at the critical perspective here. Because whenever we talk about biotech and food, it is very easy to overhype the technology and pretend it's magic. We need to look at the scientific and practical limitations of this bioprocessing platform.
For sure.
Let's clarify this for you, the listener. We are not creating literal biochemical clones of olive oil, right? I mean, if someone puts this upgraded seed oil under a mass spectrometer, they shouldn't expect an exact atom-for-atom replica of olive oil.
This raises an important question, actually. You are absolutely correct to point that out, and the paper is very rigorous about stating these limits clearly. We are creating what is called a functional analog, not a biochemical equivalent.
Functional analog.
Yes. It will act like olive oil in the frying pan. It will provide highly similar cardiometabolic benefits in the human body, but it is not chemically identical to something squeezed from an olive tree in Italy.
And there are limits to just how much health benefit we can claim.
Right.
At the end of the day, a restructured fat is still a fat.
Yes. Enzymatic interesterification is incredibly powerful, but fixing the tag structure alone does not guarantee human health outcomes in a vacuum. The nutritional significance of that structural change has to be viewed within the context of a whole diet.
Yeah, you cannot deep fry junk food in this engineered oil every single day and expect it to magically transform into a health food.
Exactly. It's a better foundation, but it's not a cure-all.
And you mentioned regulatory hurdles earlier. How big of a problem is that for the microbe side of things?
Oh, it is massive. When you start adding bioactive-rich biomass extracts from yeast and microbes into the global food supply, regulators absolutely scrutinize it.
Right, as they should.
Proving that it is safe, stable, and palatable over a 12-month shelf life in a grocery store is a massive, incredibly expensive hurdle.
But even with those regulatory hurdles, the paper argues the true genius here isn't just making one specific fake avocado oil or one fake olive oil.
That is the big takeaway. The true intellectual merit of this research is the modularity of the platform itself. Yes. It does not rely on one single organism or one specific enzyme or one fractionation step. It is a highly flexible, interchangeable toolkit. You can combine different enzymatic tools and different microbial breweries to tune oils for whatever local manufacturability you need based on what grows locally. It is a profoundly compelling model for food bioprocessing in a resource-constrained world.
So to summarize this deep dive for you, learner, science has basically mapped out a modularly scalable way to turn the cheapest, most abundant crops on the planet into designer edible lipids.
Yep.
They are rearranging the molecular couches so our bodies digest them better, and they are using microscopic yeast breweries to infuse them with premium antioxidants, all while using gentle molecular-level factory processing to keep costs viable.
And this isn't just about the cooking oil you buy in a bottle. This technology could very soon be the hidden backbone of infant nutrition formulas, medical foods for hospital patients, and sensitive formulation oils. It is about delivering premium health benefits to the global population without the premium price tag.
Which leaves us with a truly massive implication to chew on.
If we connect this to the bigger picture, if this biocatalytic platform completely succeeds at scale, it entirely divorces premium nutritional quality from geography and rare feedstocks.
Wow. Think about that for a second. You wouldn't strictly need the Mediterranean climate to easily access the core health benefits of the Mediterranean diet.
Exactly. If any region in the world can brew a functional analog of the world's finest oils, using their own local cheap seeds and a few customized microbes, how will that disrupt global food trade? And perhaps more philosophically, will it fundamentally change our cultural definition of what makes a food authentic?
That is a wild thought to leave on. The next time you grab that bottle of basic, cheap vegetable oil from your kitchen pantry, just imagine the tiny molecular couches inside and realize that very soon, a microscopic brewery might be rearranging the furniture to give you the best oil on Earth. Thank you for joining us on this deep dive, learner, and as always, keep questioning the everyday things around you.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.